Hi, it's Mrs. Walsh, and this is our first lesson for Unit 7 on the Pythagorean theorem and the converse to the Pythagorean theorem. So we're going to prove the Pythagorean theorem, and then we're going to use the Pythagorean theorem to solve real-life problems, such as determining how far a ladder will reach. Just a brief history lesson. Around 6th century BC, there was a very famous Greek mathematician named Pythagoras, and he founded a school where they studied philosophy, mathematics, and science. And many people believe that an early proof of the Pythagorean theorem came from this school. Today, Pythagorean theorem is probably the most famous theorem in geometry, and I would say hundreds of proofs now exist, and we're going to talk about a couple of them. So you should know this. The Pythagorean theorem just states that in a right triangle, and be careful, it's always in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the legs. You've learned this as a squared plus b squared equals c squared. It's just when you square the legs and add them together, it should equal the square of the hypotenuse in every single right triangle. Now, there are many different proofs of the Pythagorean theorem. Let's talk about one. If you're given a triangle ABC, and let's call this OA, capital A, B, C, and we're being told that BCA is a right triangle. I want you to prove that A squared, which is the side across from angle A, plus B squared, which is the side across from angle B, is equal to C squared, which is the side across from angle C. And I'm giving you a hint as to how to do this. My hint is that you should draw an altitude from here to here, all right? Call this point D. You should draw an altitude there and then use the geometric mean theorem. And if you'll remember what that is, that was when we were saying things like, oh, short side is the hypotenuse, hypotenuse is to short side as hypotenuse is to short side, the sevens, the geometric mean theorem, to then see what you can find out. So I want you to pause the video here. I want you to give it a go with this, maybe call this E and this F. Give it a go with this proof, and then once you've tried it, and please try it, then I want you to restart it and see what I came up with. All right, so let me remind you of the picture, because this is hard to do without the picture, where I've got A and B and C, and that's my right angle, and then I drew this down and I got a new point D. This whole side here is little c, this side is little a, this side is little b, and I'm going to call this E and I'm going to call this F, just the point from A to D and E to F. Okay, so I drew the perpendicular bisector, the perpendicular, which is an altitude from C to AB, and you're just allowed to do that. Okay, now, then you can see I use the geometric mean theorem. So in this case, I am saying hypotenuse is, we'll call this the long side, as hypotenuse is to the long side. So you can see C is to A as A is to E. C is to A as A is to E. And then we can also go for the other way, right? And we can say that C is to B, hypotenuse is to short side as hypotenuse is to short side. So that C is to B as B is to F. And once we do that, then we can cross multiply, and we get CE equals A squared and CF equals B squared, and that's because of the cross product property. Now, once we do that, we can then also, just using the addition property of equality, since these two things are equal, we can add them to both sides of this equation and not mess up the validity of the equation. So using the addition property of equality, we're going to add CF to both sides, which we're calling B squared there. Now we can use kind of the reverse distributive property here and factor out a C. And so we get the C times the quantity E plus F is equal to A squared plus B squared. But we know what E plus F is. E plus F is C. We know that. So we're just stating there that E plus F is C because of the segment addition postulate. So now we can substitute C in for that, and that becomes C squared. And voila, we've got the Pythagorean theorem, and we have proven it. So now I'm going to also show you a more visual proof of the Pythagorean theorem. Okay, so this is set to music. Bear with me here. This is just kind of a cool visual proof of the Pythagorean theorem. So you can see they start by constructing a right triangle. And then you can see that that's the hypotenuse. That's the hypotenuse. So now you've built a square that is the size of the hypotenuse. It's c squared. And now you're angling that in such a way that the short side plus long side, short side plus long side, you've made two squares that are equal. But you can see that if you collapse those two together, and you end up with four squares that are the same size, then you subtract out all the things that are the same. Those two overlap, and you can visually see here is we have the visual proof of this. So if this is like side, whoops, sorry, I did not mean to do that. So let me play this again. Let me move it back a little bit. Okay, so you can see that what we have here is this side is, whoa, hold on, I'm sorry. I'm going to bring it back because I really want you to see this picture. Okay, so let me pause it. All right, so now you can see that what we have here is this is A, and this is B, and this is C. And this is A squared, and B squared is equal to C squared. And since those two were the same, we proved in the previous picture there, as we brought them together, let me see where I can get it for you here. So as we brought them together, you subtract both of those out because those are the same, and you can see that this is C squared, and it's going to be equal to A squared plus B squared. Okay, so now back to using the Pythagorean theorem. Now that we've looked at proving it, let's talk about using it. There is something called, and I don't know how many of you guys are familiar with this, something called a Pythagorean triple. And it's a set of three positive integers, a, b, and c, that satisfy the equation a squared plus b squared equals c squared. So for example, 3, 4, 5 is a Pythagorean triple because 3 squared plus 4 squared is equal to 5 squared. All right, so if we're just trying to find the length of the hypotenuse of a right triangle, and then we're trying to tell whether the side lengths form a Pythagorean triple. So obviously, to do this, we just square 5 and 12. We get 25 and 144. And when we take the square root of 169, we do get, because I take the square root of both sides, we get 13. And since these are all positive integers, they do form a Pythagorean triple. So another Pythagorean triple is 5, 12, 13. And most right triangles have side lengths that do not form Pythagorean triples. So we're really happy when one of those comes along, but it's not very frequent. Okay, so you don't really need to see these. We know how to do this. Okay, so and we're not going to think about negative square roots now, not to algebra 2 when we get to imaginary numbers. Okay, so now if we're trying to find the length of the leg of this triangle, and as you can probably guess, this one may not come out so neat and clean. How do we do this? Well, it's the same concept, only this time we don't know one of the legs. So it's 14 squared is equal to 7 squared plus x squared, and we can do that because of the Pythagorean theorem. And then we're going to multiply those out. And then we're going to simplify. And then we're going to take the square root of both sides. And then we are obviously going to simplify our radical, which 147 is square root of 49 times square root of 3, which will simplify to 7 rad 3. And so in example 2, I am most often going to ask you to write it as a radical in simplest form unless it's a real world problem where we would want a decimal approximation. And if we put this into the calculator, it would be approximately 12.17 rad 3. And that's helpful for real world problems, but most of the time I'm going to want you to be precise by using simplified radical form. Okay, so now finding the area of a triangle. You can find the area of a triangle to the nearest tenth of a meter. You're given that the base of the triangle is 10 meters, but you do not know the height. But because this triangle is isosceles, we know it's going to be two congruent triangles when we draw this height, when we draw this altitude down. So then we can use the Pythagorean theorem. So this side will be 5 and this side will be 5. We can use the Pythagorean theorem to get h, and then we can use the formula. So once again, I told you this is 5 and this is 5. Substituting in, we get that h is equal to rad 24. And so now to find the area of the original triangle, we're just going to use the equation 1/2 base times height. And so in this case, it's 1/2. The base is now the whole base, 10. The height is rad 24. And we could have either called this 5 rad 24, or we could simplify rad 24 to 2 rad 6, right? So we'd call it 10 rad 6, or we could approximate it to 24.5. All right. So, okay, so the converse of the Pythagorean theorem. Like we found with a lot of theorems we've learned, there's a converse to the Pythagorean theorem, and we can use that to solve problems as well. And we can also use side lengths to classify triangles by their angle measures. So you already learned about the Pythagorean theorem, where if a triangle is a right triangle, then the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. The converse is also true, which basically says if you have a triangle and you don't know whether anything about the angles, but you know that this squared plus this squared equals that squared, then guess what? This is a right triangle, and you can state that definitively. So whereas the Pythagorean theorem states if you know you have a right triangle, then a squared plus b squared equals c squared, the converse of the Pythagorean theorem states if you do not know this is a right triangle, but a squared plus b squared equals c squared, then you can deduce that it's a right triangle. All right, so for example, these triangles, if you eyeball them, might appear to be right triangles. And we've talked a lot about the dangers of eyeballing triangles or any sort of shape or anything in geometry. So let's figure out whether or not these are right triangles. So with this first one, we're going to let C represent the length of the longest side, because the hypotenuse is always going to be the longest side. Square root of 113 is the longest of these sides. So now we just need to see. We'll call this A, and we'll call this B, and we'll call this C. We're trying to see, is this true? Is a squared plus b squared equal to c squared? So is the square root of 113 squared equal to 7 squared plus 8 squared? And of course, when I square those, I get that, and when I add them together, I find out it's true. So I can, in fact, yes, deduce that this is a right triangle. All right, now let's look at the other one. You can see that this looks like the largest side. So we're going to test again to see if a squared plus b squared is equal to c squared. We're going to square all of the sides. And remember to be careful when you're squaring a number times a radical. We square the radical and we square the number. So this is going to become 16 times 95. Come on down. And then when you check it, you can see, although it's very close, close does not count. It must be exact. So this is not a right triangle. All right. Now, in terms of classifying triangles, sometimes it's hard to tell from looking at a triangle whether it's obtuse or acute. And these theorems that we're about to go through can help you tell. Called another kind of triangle inequality theorem, and it says the square of the length of the longest side of a triangle is less than the sum of the squares of the lengths of the other two sides. If that is true, then the triangle is acute. So if this is the longest side, we're basically saying if a squared plus b squared, if the square of the length of the longest side is less than, so this would be less than, I'm sorry, less than. So if these two added up are greater than c squared, then we know we have an acute triangle. So if c squared is less than, this is just turning it around, a squared plus b squared, we know it's acute. And that makes sense because with an acute triangle, you're going to tend to have side lengths that are a little bit more in line with each other than when you go, with a big obtuse one where you've got it like that. So in this case, we're saying if these two squared are bigger than that last one, then it's an acute triangle, and that makes sense. Now, if the square of the length of the longest side of a triangle, if c squared, is greater than the sum of those, a squared plus b squared, if this one's so big because it's a big obtuse side, then we know it's an obtuse triangle. So in this case, if c squared is greater than a squared plus b squared, then we know triangle ABC is obtuse. All right. So now, if given three side lengths of a triangle, we can determine whether it's right, acute, or obtuse. So in this case, we're going to use the triangle inequality theorem to confirm each set of numbers. First, we have to make sure they can make a triangle. So if you'll remember, that means this plus this has to be greater than that, this plus this has to be greater than that, and this plus this has to be greater than that. We really just need to look at the two smallest if they're greater than the largest, and they are. And in this case, are the two smallest greater than the largest? Or, but in this case, if you add, yeah, so the two smallest are greater than the largest, and we're fine. So these all do make triangles. Now we have to compare the square of the length of the longest side with the sum of the squares of the two shorter sides. So in this case, the first triangle, if we square 86, which was the longest side, and see how it compares to the square of the other two sides, you can see here that c squared ends up being bigger than a squared plus b squared. So this triangle is obtuse. Now, if we look at the other triangle where 37.5 squared was the largest side, and we're looking at 10.5 squared plus 36.5 squared, when we get all the way down and look at it, we notice that the square of the largest side is less than the sum of the squares of the two smaller sides. And in that case, we can then conclude that this triangle is acute. Okay, and then finally, in construction, I'm trying to give you a real-world example here. Let's say you're trying to mark a foundation of a house. This is a picture of that foundation. And let's ignore the diagonal for a moment. Let's say your friend measures the sides and says, this is 30, this is 30, this is 72, and this is 72. We don't know anything about the diagonal yet. And says, okay, you've got a perfect rectangle for your foundation. Is he correct? So I want you to think about that a minute. Seems like that might be right. Well, in fact, it's not. Because think about it. It could be a parallelogram that looks like this. Aren't those two the same, and aren't those two the same? Parallelograms have opposite sides that are the same length, but these angles are not right angles. So this is not a rectangle. And so just knowing those side lengths does not tell us that it is in fact a rectangle. So now we are trying to say, okay, let's put the diagonal into the picture. Let's say I measure the diagonal. So now I know the side lengths and the diagonal length. Now can I tell whether this is going to be a rectangle? Well, if you think about that, we can really go back to the converse here of the Pythagorean theorem. Because if I can find that this squared plus this squared equals that squared, then I know this to be right, I know this to be right, I know them all, because this would be 78 as well. I know them all to be right angles. So let's check it out. It's into two triangles. Let's compare the square of the lengths of the longest side with the sum of the square of the lengths of the shorter sides of these triangles. And when I do that, I can conclude they're right triangles, which means that I now do have a rectangular base. All right, so that is it for this lesson. I'm sorry it went a little bit over. I'll see you guys in class, next class.